All right, welcome back to our counting slides. Let's go back to where we left off, and I think I want to start off with a question for you, and this one is about counting multisets. All right, so go back to staring at this slide for a second. We want to select n objects from a set of m varieties, all right, where like the same kind of thing is indistinguishable, so the order of the same things don't matter, but the fact that we had the same thing duplicated now matters. Okay, so we came up with a formula in terms of like picking where zeros go. We made a binary string based on like what we're choosing, putting in our Easter basket or something. And yeah, here's your question now. Let's say that we've got a bunch of coins divided into 4 piles according to whether they're pennies, nickels, dimes, or quarters. So no 50-cent pieces for this example. So all those. And now the first question, do both of these please, pause the video and do both. How many ways are there to select 25 coins from the piles? Say that you've got as many quarters as you need. You can select 25 quarters if you wanted to. So infinite supply of these, but you're only going to select 25 coins. So that's your first question. And then, how many ways are there to select 25 coins if you got a constraint? If 5 of them must be quarters, all right? And then do remember that when you're trying to solve this one, that we're assuming that all the same coins of the same type are indistinguishable. So like you're picking 5 quarters and it doesn't really matter like which of the 5 quarters, were they shiny, were they dull, they're indistinguishable. So that's going to help with the answer. So give those a try. And then assuming you're back now and you gave it a good try, shame on you if you're just continuing with the video. Please try it. I promise it helps. Let's try to do it. So here, how many ways are there to select 25 coins from the piles? Well, this is just a multi-set question, right? You're going to turn this into a binary string. Like I want to select, like in this order, pennies, nickels, dimes, quarters. So I've got, maybe I'll select 3 pennies and separator, because now I'm going to pick choose how many nickels to pick. Like maybe I'll pick 1, 2, 3, 4 nickels, and then I'm done. So put a 0. And then 1, 2, 3, 4, 5 dimes, and then maybe I'll make the rest quarters. So it's the ones have to add up to 25. But like, do you see what you're kind of building there? And so this could be turned into this kind of check. Like I'm building up a string of size n plus m minus 1, where n in our case is 25 coins, and the m is the number of varieties, so it's 4. So I'm building up a string of size 25 plus 4 minus 1, because there's one less number of zeros, right? So that's this formula now. So n plus m minus 1, choose m minus 1. And that's my answer. That's just a standard multi-set counting problem for the first one. n plus m minus 1 over m minus 1. Or choose m minus 1, sorry. Which is going to be 25 plus 4 minus 1. So 25 plus 3, size 28 string. And you're picking the indices, the 3 indices where the zeros need to go. So that is the number of ways, all right? And now, the next question looks hard, but it's not as hard as you think. All right, so how many ways are there to select 25 coins if at least 5 must be quarters? So you're going to force and make sure that there's going to be 5 quarters. You want to grab 5 quarters right now and then deal with the rest. Do you see how you can do those separately? So like, how many ways are there to grab 5 quarters? Like do that first, where the 5 quarters are indistinguishable? There's just one way. Does that make sense? If we're considering all the same things, all of the same type to be indistinguishable, it's like, doesn't matter that they were like recent, shiny and new 2025 quarters or something, or like old 1960 made of silver quarters, like there's still only one way to pick 5 of them. If we consider them to be indistinguishable, there's only one way to pick 5 quarters. So like, make sure you've got 5. Go do that. Get a handful. Do you see how there's one way to do that if we consider them to be indistinguishable? To pick 5 quarters. And then you multiply that answer by, like, all right, you've picked 5 things. You want to pick 25 total. So now the question is like, all right, you can still pick some more quarters. You just had to have at least 5. So we'll start with 5, and now you've got 20 coins left to choose from. Does that make sense? So it's like 1 times all the ways to select 20 coins now. There's 20 left from all the piles. You can still choose more quarters. You just had to have at least 5. Do you see how that would solve the problem? From the piles. Does that make sense? And so like that's the final answer. It's like you're choosing 20, choosing from 20 things, because like your hand has been forced for the first 5 quarters. And so that's going to be equal to 20 plus 4 minus 1, choose 4 minus 1 again, It's got fewer slots to fill in because like your hand has been forced. You're making sure you got 5 quarters at the very start. You can have more, but at least 5. So that turns into what? 23. Choose 3. All right, so it's a slightly smaller number than the first one because you have less choice. All right, that's fun. So okay, there's that one, and now here's a new topic. It's called the principle of inclusion-exclusion. It's a long name, but it'll make a lot of sense. All right, so when sets don't overlap, just like our sum rule, if you want to figure out the size of their union, you'll just sum sum their individual sizes. So like if this is S1, it's got some stuff in it, and this is S2, and they're disjoint, right? You can see that what's the size of the union of the sets? Just like the size of S1 plus the size of S2, that makes sense. But when they do overlap, it's not as easy, right? So if this is S1 and this is S2 and they share some stuff, then we have a problem, all right? They got some stuff shared by both of them. You can't just add them both because now you've double counted this stuff, all right? And so there is a general principle that like works for like any number of sets that might have things in common. It's called the principle of inclusion-exclusion, and that's the way of counting the size of a union of sets in the face of overlap, all right? So for finite sets and size 2, for just 2 of them, the formula is this. A union B, the size of that is equal to, and this works in general, even if there's no overlap, this would be the empty set, right? The size of A plus the size of B minus the size of their things that they have in common, because then you would have double counted. I hope that makes sense. So in general, here's an A. Let's do this and spell it out and watch it work for just a simple example. So there's a set A, there's a set B, and let's say that A is size 6. All right, and then B is size 5. All right, but they have 2 things in common between the 2 of them. And so in general, the size of their union, we know the answer is going to be, what, 9? Let's watch it come out of the formula. It's equal to the size of A plus the size of B minus the size of what they have in common. Because if you think about it, their intersection. If you think about it, like you're double counting. You count all these guys, count all these guys. You've now counted these guys twice, the common elements twice. So subtract one count of those common elements. See it? So that's going to work out. So like 6 plus 5 is 11, minus what they have in common, 2, so 9, because you would have double counted. See that? So it gets much, much worse when there's like you got 3, 4, because then you got like, oh gosh, it's disgusting. Because then you got like individual overlap among some of these sets, like just these guys overlapping, and then you have stuff in the middle of them all overlapping. I need to draw this better. Sorry, it's so small. All the room I've got. It's like you can have them all 3 overlapping, and have just 2 overlapping. There's a lot of different issues, and then like if you add them all up, you've somehow overcounted and also undercounted. So like the union gets disgusting, right? The size of their union in general is the size of the individual pieces minus the size of like the size 2 intersections, like this guy and this guy and this guy. But then once you do that, you've now undercounted what they all share, and so you got to add that back in. It's very disgusting. So there is a pattern. I'll leave that to you to read that in the book. All right, it's too much to write down. So that's the principle of inclusion-exclusion, though. It gives you a formula for that, okay? And so, yeah, let's keep on trucking. Let's talk about, like, generating. Like, maybe you'll want to write a program about this. I'll force you to do it eventually, to generate permutations and combinations. And so if you want to generate, like, all the permutations of a set, all the combinations of a set, usually you want to do it in some nice way, and the nice way that we like to use is called lexicographic ordering, which is just a very like snooty way of saying dictionary order. This is like the lexicographic is the adjective form of the word dictionary in Greek. So there's that. So all the strings in your programming languages have been compared in lexicographic order. If nobody told you that word before, that's what's happening. Like if in C++ even, like you can compare the string ABC to the string BCD, and this is true, right? This will give back true because ABC comes before BCD in the dictionary. Does that kind of make sense? And same for these guys. Like ABC comes before ABD in the dictionary because even though these two, like the A's match, the B's match, it's like, all right, you try the next ones. Like, all right, which one comes next? And so like C came before D, so like this is smaller. It's really doing ASCII order inside of C++, like for some weird reason. Like the percent sign is going to be like less than other characters, like less than the letter C, for example. Like weird things happen like that, but don't worry about it too much. Numbers and like special characters ruin things, but there is an order. We can give an order to everything, and it's like dictionary order with some extra orderings for characters that are digits and special things. So we have some algorithms in our textbook that will tell you how to generate like every permutation of a set or every combination of a set, and it gives them to you in lexicographic order, which is just a nice order that makes sense. All right, and so I'm going to force you eventually to implement these functions. All right, so we need to talk about them. These are algorithms now. All right, so let me teach you these algorithms, and we will figure them out together. All right, so here's the algorithm to generate all the permutations of a set, all right, in lexicographic order. Generate every single permutation of a set, okay? There's two functions. They're working together, all right? So this is the main one, and it's a bit more generalized. So this one is generally, or it's a bit less general, actually. So this one's called genlex permutation, and you give n, and so it's like your hand has been forced. So what it's going to do is going to generate all the permutations of a set from 1 to a number n. All right, so that's what this function does. You can have it generate permutations of anything by using those numbers as indices. All right, so this still works very well. So generate all permutations of the set 1, 2, 3, all the way to n. All right, that's what this function is going to do. It'll give you back all of them in lexicographic order. That's what the n parameter means. And yeah, we need to talk about it. So it's pretend, for example, you give it like all of the letters in the alphabet. You can like give me all the permutations of that. Like it'll give you ABC. That's the first permutation in lexicographic ordering, and then like the last one is ZYX all the way down to A. Do you kind of see how that's going to be? Like those are all the permutations of all the letters in the alphabet. Like this would for sure be the first one, the letters in order, and then the letters backwards would be the last permutation that it gives to you. All right, so this function kind of makes sense. It uses this helper function that we need to explain in detail, but this one just like takes a permutation, gives you back the next one, gives you back the next permutation. So yeah, what you do is if you're going to make all the permutations of this set 1 through n, the very first one is the numbers in order from 1 to n. That's your first permutation. So output that one. And then, as long as you're not the last permutation, like the numbers backwards, or Z down to A, you see how that's your last permutation. As long as you have more to do, like you're not on the last one, then take your current one, plug it in the next permutation, because that'll take this one and give you the one right after it in lexicographic order. That's the purpose of that function. Gives you back that one, update it, and then output the next one. So like keep on outputting the next one until you hit the last one, then you're done. Does that kind of make sense? So this function should make sense, all right? But the way that we take an input permutation and then compute an output permutation, that's the next one in lexicographic ordering, is very weird, all right? So we have to talk about it. It's like, feel free to read this, like let k be the largest index such that pk is less than pk plus 1. If no one exists, then it's the last permutation. Like read this. It's a little weird, all right? It's hard to understand. So the best way to show you the answer, show you what it's doing, is to draw some pictures. So you're going to implement this. You're going to turn these words into code. It's not the easiest thing though, all right? So let's talk about it. Let's say that n is 5. All right, so the very first thing this function does is initialize the very first permutation to be 1 through 5 in that order. 1, 2, 3, 4, 5. Okay, in that exact order. And we can think about this as like a string, right? A string of digits. They have indices 0, 1, 2, 3, 4. All right. And so what we do is like we print that one. That's the first one. It's not the last one yet. It's not 5, 4, 3, 2, 1. So let's shove this exact one. Let's give it to next perm, and have it update. Have it give me a new one. All right. So let's watch it work. Okay. So we're working with indices now. So this is where they come from. These are the indices of these numbers in this tuple that we're constructing. That is our current permutation. So what we first do is we find the largest index and call it k, such that p of k is less than p of k plus 1. So it's like compare the thing at an index to the thing right after it and make sure that it's still smaller. So find me the largest index where the thing after the thing at that index is bigger. So like look at all these guys. That could be like set k to 0, try it. Is the thing at pk less than the thing at pk plus 1, the thing right after it? Yes, so that's true, because 1 is less than 2. Does that kind of make sense what it's doing? Let's going to try these guys. 2 is less than 3. 3 is less than 4. 4 is less than 5. And we find the biggest k for which this works. And so do you see how 3 is the biggest k for which this holds? That's the answer. That's what it starts with. So that's our pk. That's what it does. All right, it's very weird. But this will do it. This will do it in lexicographic order. So we found one. So this wasn't the last permutation. The biggest index such that that is true. Like the thing after it's still bigger than us immediately after. And then, all right, let's find another thing. Let pj now be the smallest element such that j is bigger than k. So only consider the ones right after that index. So these are the only things that we can consider is this thing in index 4. Find the smallest element that is bigger, like it comes after index k, and also the thing that is there is bigger than the thing in index k. It's like this is the only thing we have to choose from, and it's going to work out. So it's a bigger index because k is 3. It's index 4 is bigger, and then also the thing that we see actually at that index is bigger than the thing at index k. Does that make sense? You got to stare at it for a while to have it have you fully understand it, but that is our j. P of j is that element. Okay, so that's what we found, and then we swap them. Swap pj, pk. You swap the guys. So we're gonna produce, right? 1, 2, 3, not 4, 5. We swap the elements. 5, 4, and then also we will reverse the order of everything after index k. Pk plus 1 all the way to the end. So like from 4 onwards, reverse everything. That's already reversed. It's just the number 4. So that's fine there. That one's happy. And that's our next lexicographic ordering permutation. So 1, 2, 3, 4, 5, then 1, 2, 3, 5, 4. That's the next smallest one. Does that make sense? That's the secret. All right, and let's try the next one. All right, so now again, we're going to find indices. All right, so okay, again, let k be the largest index such that pk is less than pk plus 1. All right, so we're going to go scan through and look at things right next to each other. pk plus 1. So like those guys are less than, so k could be that one. The first thing, that's true. That's true. And then 5, 4, it's not true. The thing after is smaller, not bigger. So this is the last time it works out. Does that make sense? So k could be this element. pk could be that element. So index k could be like 2. Does that make sense? That is the largest index such that this is true. The thing right after me is still bigger. Immediately after me is still bigger. So that's my pk. All right. And then again, all right, let pj be the smallest element. Sorry, smallest element such that j is bigger than k and pj is bigger than pk. So I forgot if I said smallest element before. That's very important as well. So it's coming afterwards, and it's still got to be bigger than the thing at pk. All right, so let's think about this. So we have these things to choose from. Those are the things after index k. Like that checks out this. And then also those things, we want them to be bigger than pk. Right? What are all the things bigger than pk? They're actually all bigger than pk, so we're good there. We're set. And then also, we want pj to be the smallest of all those options that are still left. So what are the smallest of these options? 4. That's how we choose that pj is the one, is that one. You see that? Okay, that's the answer, all right? And then we swap them. We swap pj and pk, and then we do this reversal, and so we actually have to do something now. So let me use green to show like the scratch work. So we're going to swap them. It's going to be 1, 2, 4 and 3 get switched. So it's 4, 5, 3, all right? But actually this is a little too big. This is not the next one, so we still have some stuff to do. So what we do is we reverse the order of pk plus 1 through the remainder to the end. So this was index k. So after that one, pk plus 1 onwards are these guys, and then we reverse them. All right, so it's the 5 and the 3 we reverse. That does not look like 5 to me, so let me replace that. So you take them, and you reverse them, and you turn it into 1, 2, 4, 3, 5. Do you see how that is smaller? Like, consider these like, this is totally smaller than this guy, right? Because 3, 5 is smaller than 5, 3. It's like 35 versus 53 kind of. Think about them in terms of numbers if you have to. But like, that's the next one. It comes after this one. 1, 2, 3, 5, 4 turns into 1, 2, 4, 3, 5. See that? It's the next thing that could happen. And so that's how you give back and compute the next one. 1, 2, 4, 5, 1, 2, 4, 3, 5. And that's what we got from doing all our little scratch work. And then you can like keep going. It's a very good example and practice to keep going and try the next one. All right, so try that, and yeah, I think that's the answer. So you're kind of seeing what's happening in next perm. Give it a try with this. All right, let's say that we're permuting the numbers from 1 to 7, and here's the current one we're at: 1, 5, 4, 7, 6, 3, 2, 1. Try to find the next largest one. What is the next one in lexicographic ordering? So run this code again for it, please. All right, do you see it? So what's our PK? So like consider all these guys. That one doesn't check out. Okay, that one, the next thing is bigger. Cool. That one, the next thing isn't bigger. Same with these guys. Like you try them all. This one doesn't work. That one doesn't work. The biggest one, right? Maybe you should try from the rightmost end, where the thing to the left is bigger than the thing immediately to the right, is this one. Do you see it? It's 4 and the 7. So way over here, that's my PK. You see it? And then now we got to find the matching PJ. All right, so PJ needs to be the smallest element such that J is bigger than K. So all right, let's whittle down our elements. So okay, we got all these guys to choose from. So these are our valid options right now to choose from, because their index is bigger than K. So all the things to the right. So that's true. And we want all the things to be bigger than the thing at index K. Those are my valid options still. So what's all the things that are bigger than 4? So it can't be the 1, can't be the 2, can't be the 3. So it's the 7 and the 6. Those are my new options. All right. And I want the smallest option. J be the smallest option such that those things are true. So the smallest one, do you see how that's going to be the 6? That's this guy. That will therefore become my PJ. Does that make sense? That's the answer. And then we swap them. Right? The next thing is swap them. So it's going to be 5, 4, sorry, not 4, but 6, 5, 6, 7. And then comes the 4. We swapped them. Then the same 3, 2, 1. All right, but we're not done. Then we have to reverse. Reverse the order, because then it's a little too big. Reverse the order of everything after index K. So index K was this one. Index 1, the second thing. So all these guys, from here onwards, we reverse because it's too big. It's backwards right now. And that's just kind of how the algorithm works. This all becomes like backwards, then you reverse it after you do your swapping. So this means the next one, really, the next permutation is 5, 6, 1, 2, 3, 4, 7. Do you see it? There's your final answer. So the one after, 5, 4, 7, 6, 3, 2, 1. Like we've used up all the 5 4s. We have to go on to the next one. It's going to be 5, 6. 5, 6. And then the smallest thing you can put here with the remaining element. That's kind of how you think about it. All right, but that's the algorithm. Do you kind of see how it's working? Like you whittle down your options. And that's the next one. Okay? There's that. And that's how you generate all of the permutations of a set in lexicographic dictionary order. All right? So that's how that works. Let's do the same for generating all the combinations, all the subsets of a given set in lexicographic order again, right? So again, we've got a function and it's working with numbers, but you could bring it back to anything if you just use those as indices. But what this function does is it's meant to generate all the subsets that are of size R, of a size n set. Generate all the subsets of size R, I don't think that subsets is legible, sorry. Generate all the subsets, it's hard to write with a tablet, guys, of size R from the original set that goes up to n, 1 to n. That's what this is going to compute, 1, 2, 3, n. And so order is important because we're generating these subsets in lexicographic order. So when it says output S and like S starts at this, like keep the order, don't jumble anything. Think of it like a tuple, really. That's what it's going to be in code anyway. So it's like a vector. So initialize S to be this. This is your first set, 1 plus 2 all the way just to R. That's the smallest one. And then you output that. And then the last biggest one is at this one. All right, it's because the order doesn't matter, it's still going to be ascending, but it's n minus r plus 1 all the way to n, all the remainder elements, all right? It's a size R set still. So as long as it's not that one, you got one more to do. So calculate the next one, given the current one and the number n, calculate the next subset and output it, all right? So this function again makes sense, but like the devil is in the details of this next subset function. How does it take the size and then the input set and then compute somehow the next bigger one, the next bigger subset. All right. So again, it's finding indices. It's disgusting. Let's again have an example. All right. So let's say we want all the size 3 subsets of a size 5 set. All right. So we would like to give all the size 3 subsets of the set 1, 2, 3, 4, 5. That's what we're doing here. Okay. So what the function does is it starts off with 1, 2, all the way to r. So in our case, 1, 2, all the way to 3 is the very first one. Does that make sense? 1, 2, 3. That's our first subset. That's the smallest size 3 subset. In ascending order, it's all making sense, I hope. And the last one, we're going and we're doing this as long as we're not this one, n minus r plus 1, all the way to n. If you think about it, what's n minus r plus 1? 5 minus 3 plus 1 is, excuse me, 5 minus 3 is 2, plus 1 is 3, right? So that means the last subset. I blanked. It's hard to do arithmetic when we're thinking about hard math. 3, 4, 5. Do you see how that's going to be the largest size 5 subset? Because order doesn't matter. Or sorry, size 3 subset of a size 5 set. Do you see it? That's the smallest one. That's the biggest one. Then we're done once we get to that one. All right, so we have to eventually get to there. All right, so now we do it. All right, so now, again, we're finding some indices. So, okay, let k be the largest index such that s of k, the thing at that index, is less than n minus r plus k. So that's always going to be important. N minus r plus k. N minus r plus k. That's very important for us. The k is going to change, but the n and the r are always going to be these. So for this example, at least, so it's always 5 minus 3 plus k. That's an important thing that we care about. All right. So this is index, and the indices start at 1 here. This is index 1, index 2, index 3. That's also very important. The indices start at 1 for this algorithm, and it's very important that they do start at 1, because otherwise these things don't work. So it compares to this number, assuming that those indices started at 1. So okay, let k be the largest index such that s of k, the thing at that index, is less than n minus r plus k. All right. So for us, when it's 1, at least, what do we see? Like S1. That's a choice, right? It could be that one. That's the thing in index 1 for us, because indices start at 1. S1 is that, what we check is S1 less than n minus r plus 1? See that? Because we chose the line there. Make sure that that's true. Is S1 less than 5 minus 3 plus 1? That's equal to 2, 3. It is, yeah. The 1 is less than the 3. So that checks out. That could work. Then you try the others, right? S2, is that less than n minus r plus 2? S2, is that less than 5 minus 3 plus 2, which is 2, 3, 4? And it is, yes? For sure it is. It's just a 2 right there. And then finally for S3, you also compare, is that less than, find the biggest one. Is that less than S of 3, is that less than n minus r plus 3? It's trying to compare it against the biggest thing that could possibly go in there. See that? 5 minus 3 plus 3, which is just 5. And yeah, it's 3 versus 5. Yeah, it's definitely smaller. So we're finding the biggest one. It looks like S of 3. 3 is the biggest index such that the thing there is less than the biggest thing that could possibly be there. Do you see that? So that's how you compare. So that's finally our S of k. All right. S of k. Think about it in terms of the biggest thing that could possibly be there. That's kind of what this is computing. All right, that's what we want. And then we increment the thing there. S of k becomes S of k plus 1. That's the next thing that we do. And so this is going to turn into 1, 2, 4. Do you see it? And then also what happens if there were other things, every index after index k, you're going to just take the thing that came in the index previous and add 1. So it becomes an ascending order kind of thing. We have nothing after our index k right now. There's nothing over here. So it's just 1, 2, 4, call it a day. All right, so that one's done. So that 3 became a 4. And that's it. The rest is done. You return, that's our next subset. So 1, 2, 3, 1, 2, 4 is the next one after it. Oops, there it goes. Okay, and then, all right, what's the next one? After 1, 2, 4, what's the next smallest subsets going in lexicographic order? So again, you're going to compare all these indices to these values. And if you think about it, just all right, is this smaller than what could be there? Could I increment that if I wanted to? Like, is 1 less than 3? Yes. Is 2 less than 4? Yes. Is 4 less than 5? Yes. So again, I found, like, find the biggest thing that could still be incremented. That's what it's saying. So that's my new SK. You see it? So that becomes 1, 2, 5. I think you can imagine how the rest is going to play out. Like, there's my K, index K, increment the thing there. The next thing is 1, 2, 5. See how that's the next smallest subset of this set, 1, 2, 3, 4, 5? I hope you see it. All right. So again, yeah, you just keep playing this game. Like, all right, what's the next one after this? You feed it back into this. Remember that the indices start at 1. That's very important. And then, yeah, find, like, K be the largest index, so that this is true. Is S of 1 less than 3? Yes. Is S of 2 less than 4? Yeah, it is. That one checks out. Is S of 3 less than 5? No, it's equal to 5. So that one we can't increment. We want the biggest one that we still can increment. That's the biggest index that we can still increment, that one. So there's my S of K this time. See it? So now I have something to increment. So that's that one. So increment it to make it, what do we do? So this becomes the set 1, 3. Now we incremented the 2 to 3, and then what the algorithm is saying, what comes after has nothing to do with what was there already, actually. That's 1, 3, and then what comes after is, for every index afterwards, the thing that we place there is the thing in the previous index plus 1. So you take this 3, you increment it to make 4. That's what it's doing. It's placing it in ascending order. That's how you build it. Does that make sense? That's what that algorithm is doing. That's what these words mean. All right, that's why examples are very important here. So I hope you see it, and then now you can kind of, like, we get the hang of it. All right, the next one has to be 1, 3, 5. And then what's the next one? Then we've got, well, okay, 1, 3, 5. 1 could be bigger, 3 could be bigger, 5 cannot be bigger, so it's this one. That's my SK again. S of K, I'm going to increment it to be 1, 4, and then whatever comes after is this guy, like, incremented. So always increment the thing before you as you fill in the rest. It's just in ascending order. Now it's 1, 4, 5. Does that make sense? And then again, like, all right, this is the next one. It's not the end. It's not 3, 4, 5 yet. So, all right, let's keep on trucking. So find this. Find this K index again. So is 1 less than 3? Yes. That could be the K. Is 4 less than 4? No. Can't be K. Is 5 less than 5? No. Can't be K. So the biggest index and the only index now that could be my K is this one. This is my SK. It's 1. So follow the algorithm by incrementing 2. Yeah. And then everything that comes after is like that one plus 1. So 2 becomes 3. And then the thing that comes after is the thing before plus 1. So 2, 3, 4. That's going to be how it generates the next smallest subset. Does that make sense? And then it's going to keep on going in that manner until it gets to 3, 4, 5. You can imagine the next one is 2, 3, 5. Yes. So that's a lot of work and a lot of thought, but like that's what's happening in there. That's what you're going to implement. Okay? I hope you see it. So yeah, with that, new topic. All right, that was a lot. Let's talk about binomial coefficients, which you for sure have seen before, but it has to do with like combinations. That's really cool. So let's think about it. So the binomial, b plus o, those are variables, cube it. What does this turn into, right? It's just like this. It's disgusting, but it's that. Like you foil it out. Like you can have 3 b's, 2 b's and an o, then a b and o and a b, boo, b-o-o, like all these things, right? It's like you're picking b or o 3 times. That's what the math is doing, yes? If you take the like terms back together, they got like, is b cubed plus 3 b squared o's, because you got a bunch of those the same, right? It's like there's only one with 3 b's, but there's a few with like 2 b's and an o. You got these guys, right? 2 b's and an o, 2 b's and an o there, 2 b's and an o there. You got 3 of them. You see it? And then same with the bo squares. You got like, there's b and 2 o's, there's a b and 2 o's, there's a b and 2 o's. Like you got 3 of those as well. Yeah. And then there's like only one option for just all the o's as well. It's like just that one. One option there. So really there's like one option for those, one option for those, and then 3 options for those guys, for 2 b's and an o or 2 o's and a b. But the order doesn't matter. That should remind us of something, right? So that tells us something about subsets. Do you kind of see what's going on there? So these coefficients, this 1, 3, 3, 1, for all these pieces, are called binomial coefficients, because this is a binomial thing, right? 2, bi means 2, right? You got two terms being or taken to some power, and those things are binomial coefficients, and they're also the same in reverse, and that's also very interesting. That's something we should think about. 1, 3, 3, 1 is the same forwards and backwards. It's a palindrome. And so that brings us to this idea, the binomial theorem. It just so happens that these tell us something about subsets, these coefficients, because it's like, all right, you have, how many ways are there to take two B's and one O? There's 3 apparently. How many ways are there to take 2 O's and 1 B? There's 3 apparently. How many ways are there to take exactly 3 B's? It's only 1 way. Does that kind of make sense? There's telling us something about subsets. And so yeah, the binomial theorem relates all that together. So the binomial coefficient of some term, because they always look like this, like the powers add up to whatever you're taking. So these add up to 3 always, right? So 3, 2 plus 1, right? It's up to 3. 1 plus 2 is adding up to 3. That's secretly all there. So whatever term you're looking at of some number taken, like some binomial taken to the nth power, is n choose k. And that happens to be the same as n choose n minus k, surprisingly, because of this like reversal effect. You can think about it in one of 2 ways. These are the exact same number. Isn't that neat? So you maybe have learned about this in terms of Pascal's triangle, and so we can all relate this back to combinations now. So Blaise Pascal, very important mathematician, developed a little chart that contains all the numbers that look like n choose k, and maybe you've drawn this triangle for yourself in math class before, just trying to do this quickly. But it's all coming together from the idea of like binomials. It's very cool. It can relate it all, all right? So this is Pascal's triangle, and these are just like, you start with ones, right? It's like this is 1, and then like the way that we build it, you add them up, right? You add them up together, and then you get the answer. And so like Blaise Pascal and his triangle tells us a fact about how we can build bigger combinations from smaller ones. Isn't that neat? And it's always ones along the sides, remember that? Ones along the sides, and then like you add them up, like that becomes bigger things. Like 1 plus 1, this must be 2, right? Then you add these guys. 1 plus 2, that must be 3. This one must be 3. There's my 1, 3, 3, 1. You see it? Just like we had back here. So yeah, that's something. That's something cool, and that's Pascal's identity. It just so happens that the number of ways to select a set of k items from a set of n items, so n choose k, is equal to the number of ways to select k minus 1 from n minus 1, plus the number of ways to select k plus k items from n minus 1 things. So that's showing this identity. N choose k is equal to this thing plus this thing. N minus 1 choose k minus 1 plus n minus 1 choose k. Interesting. That's an identity, we say. It's just a theorem showing that things are equal. They're identical. All right, so that's the diagram. That's why it works. That's really interesting. It's like these smaller pieces can build this bigger idea. And then we get a triangle to prove it all. It's very nice. All right, so let's, I guess I better prove that to you right now. It's like, why does this theorem check out? Like we can see it working kind of from this, but why does that work? All right, so let's figure this out together and go from there. So okay, proof of Pascal's identity, that this is true. What you do is you pretend. Let's pretend that we're counting a bunch of k subsets of an original set A. Like that's our original task, right? N choose k. K subsets of a size n set A. All right. So and then this is what the theorem is trying to tell us. All right. This is how we can break it down. I'll show that to us. So let's just have a hand wavy example. Let's say that k is 3 and n is 5. So we're trying to figure out all the size 3 subsets of a size 5 set. And just for clarity, let's make this our set. This is my set. 1, 2, 3, 4, 5. I'm trying to take subsets out of. All right. So it just, if you think about it long enough, you stare at this long enough, the ways to make all the k subsets of A, like I want to make k subsets of A, right? Size k subsets of A. It's the same as, you can split it up based on like one of the elements of your set. Think about it in terms of all the k subsets that contain A to A sub n, like that element, and then all the k subsets that don't contain it. All right. So that's how you do it. All right. That's how this identity is going to work out. So like pick a number, and we'll like split off based on that number, that element of that set. So here, let's say that we've picked 5. All right. So that's my AN or something. we can split up, right? We're trying to find all the size 3 subsets of a size 5 set. You can split it into all of the length k subsets that contain that element, that contain an, which in our case is going to be 5, and then also the length k subsets that don't contain it. Do you see how, like, if you take them both together, you have the final answer? And just like that splitting is going to make it easier for us. The length k subsets that don't contain that element. Contain an, which is 5 in our case. We're going to pick 5 to be that. So like, all right, what are all the length k subsets that contain an? So like, k is 3. So like we got 1, 2, got half 5 in it somewhere. 1, 2, 5, 2, 3, 5. All these guys. 3, 4, 5. Like there's a bunch of different options, right? All the ones with a 5 and ones without a 5. So 3, 4, 5. You got plenty more than that. But like, do you see how that's like part of it? Like there's a 5 somewhere. All the ones with 5 and all the ones without 5. Like you got, what is it? 1, 2, 3, 2, 3, 4, 1, 3, 4. Think about it in like a canonical ascending order thing, because order doesn't matter. Do you see how, like, if you had this set, if you calculated that set and that set, you would have generated what you wanted? Yes? The original number of k subsets A. So if you take the size of this set plus the size of this set, you have your final answer. That's where I'm going with this. All right? And so these are smaller things that we can find formulas for. All right? So that's what we just noticed. The size, number of k subsets of A, which is this idea, right? N choose k, is equal to the number of k subsets of A that contain an, right? So really, just pick all you're doing is you're taking a bunch of sets of one smaller thing, right? You're taking a size 4 set. Like you're just building, like find the 1, 2, the 2, 3, the 3, 4, because you're going to tack a 5 on at the end. The fact that the 5 is there doesn't really matter. Does that kind of make sense? Like we can turn this into, like, cross off the 5 and choose 2 things from a size 4 set now, because we're going to add a 5 to it later to make a third thing. Does that make a little bit of sense? So that turns into n-1 choose k-1. Because just like, to make all of these, the same count is like, don't even forget about the 5. Make a bunch of size 2 sets out of a size 4 set, because we're not considering the 5 anymore. I think that's all the different ways that I could explain. I hope you see it. Please yell at me if you do not see that. That's what I'm going with, all right? It's like, forget about the 5 for a second. It's like, how do you build this? It's equivalent to like forgetting about the 5 and building all the size k-1 subsets. K-1 subsets of a 1 smaller set, because we forgot about the 5. That's the secret, okay? So that turns into that. And then this one, all the k subsets of A that don't contain an, it's again something smaller, right? We're forgetting about that one. And then for this one, it's like, we've forgotten about 5. It's just like you're taking size 3 subsets of a size 4 set now, because we don't have 5 anymore. See how that simplifies as well? It's like, it's n-1. Now we have 4 things. Still choosing k of them, though. Still choosing 3. That's the secret. All right? That's the formula. That's the identity. Now you know it. All right. I think that's what I wanted to say. I hope that made enough sense. But that is the formula. That is the theorem. And now let's apply the theorem. So, like, all right, we can do this with binomial coefficients. So, like, the binomial coefficient of this guy in this formula is n choose k or n to the n-k. So it doesn't actually matter. Let's prove that to ourselves. So, all right, find these coefficients. Find the coefficient of this term in this binomial, and find the coefficient of this term in this binomial, please. And so I'll go back to the slide so you can pause there as well. But like, write down that, and then here's the theorem. All right, are you ready? So let's think about this. 3x, 4y, or negative 4y technically. Let's think about this in terms of like what this is telling us. Like, what's the a and what's the b in this formula right now? We've got, well, the a is equal to 3x, right? A is equal to 3x. And then the b is equal to not 4y, but negative 4y. You see it? Because it's like, it's saying plus. So we got to take the whole negative thing. The b is equal to negative 4y. Boop. And then, all right, what is what is the rest? Where do I need to be? And then what is like, what's n and what's k? So n is the power, and then k is like the exponent on the first thing. So n is 8, right? And then k is the exponent of one of these, like x. So there's the 5. So that's k is 5. So that means, all right, now we can do our stuff. So that means the binomial coefficient is equal to, you take n choose k, all right, or n choose n minus k. Either one of those is going to work. So it's going to be 8 choose 5. But that's not the full answer, right? Because it's like, here, like that's the first part of it though. Like that's how many of these there are. That's how many of those there were duplicates of. But it wasn't just a number and a number. This just wasn't just one of them, right? There wasn't just one of them each time. Each time we had an A, there were three x's. Each time we had a B, there were -4 y's, right? Do you see that? So it's not the same, not exactly the same. So there's more there. So it's not just this times x to the 5th times y to the y cubed, but in addition, like because there's 5 x's and 3 y's, that means the 3 also came along 5 times. That means the -4 also came along 3 times. Does that make sense? That's what's going on. So this is really, you also have the 3 coming along 5 times, and also the -4 coming along 3 times, because like that's what those things were taken to. I hope you see that. So that's the final answer. That's the coefficient. That's the real coefficient. Okay. And then same for this one. Let's see this one now. So okay, we've got the final answer. Like what's next to x to the 6th times y to the 1st? Well, the coefficient, the binomial coefficient at least, is going to be 7 choose the 6. Yeah. 7 choose 6, but that's not the full story because we took the x 6 times, and so that means the -2 came along to the 6th power 6 times as well. And then also same for this one. There's a -5 that came along once. That'll be this is your exponent, or not your exponent, that's your coefficient. Do you see it? That's the secret. Yeah, I think that's most of what I wanted to show you there. Oops. One last major topic for the day. Let's talk about, it's called the pigeonhole principle. It's a cute little name, talking about birds. And it's very simple, but it has some very vast implications. I love it. So the pigeonhole principle is just the idea that, like, all right, you know that there are n+1 pigeons in your pigeon coop. Like you've got n boxes for n+1 pigeons, all right? And you know that each of those pigeons is in a box, all right? You've got n+1 pigeons, you know they're all in some box. What that tells you is that there must be at least one box that's doubling up on pigeons. Yeah, that's so simple, right? That's like, it's obvious, but it's very easy to think about, right? In the worst case, all right? In the worst case, like if you had the nicest, like here are all your pigeonholes, you know that there's a certain number of pigeons. Let's say, I don't know, you got n boxes. These are n boxes. You got n+1 pigeons. Even if they spread themselves out as much as they could, they didn't have to. Like they could all be packed into one box if they wanted to be. It's still true at that point. But even if they spread themselves up out as much as they could, there's always going to be at least one box that had multiple, because you had n+1 in n boxes. You see that? So you can prove this with by contradiction. It's very simple. So just like, all right, assume that there isn't a box with more than one pigeon. All right, so that what's the opposite, right? Assume, what's the negation? Assume each box then, for a contradiction, assume each box has, therefore, less than or equal to one pigeon. That's the opposite. Then, right, the max number of pigeons in our pigeon coop, the number of pigeons is, at max, is like, well, we got less than or equal to one pigeon in the boxes. And the number of pigeons is less than or equal to one pigeon per box times n boxes, which is just n. But, right, so we've said that the number of pigeons is less than or equal to n, but we know that there's n+1. But n+1 is greater than n. There's our contradiction. So that proves that there must be at least one box with more than one pigeon. And it's so magical what we gain from that. So it's very interesting. So formally, people don't talk about pigeons. They prove the pigeonhole principle using functions and like the sizes of domains and codomains. Like here's, you got like a size 4 input set taken to a size 3 output set. You are forced to double up on one of these. That's another way to frame the pigeonhole principle. But I like the idea of pigeons in boxes. So, all right, here's what you gain from that knowledge. It's very cool. Oh, I forgot to QED myself. Very important. There we go. All right, here are some examples. So here's a nice one. If you have a drawer of 3 kinds of socks, 3 different kinds of socks, and none of them are in pairs because you're very lazy when you do your laundry, then in the worst case, and you put a blindfold on, you have to take out 4 socks, right, until you get a matching pair. Does that make sense to you? Because like here's what your drawer looks like. It's got a bunch of socks, like 4 different kinds of socks. Socks 1, sock 2, sock 3 over here. There's another sock 1, sock 3. They're all jumbled together. Sock 2. They're not all in. None of them are in pairs. In the worst case, you have to take out 4 socks to know that you have a matching pair, right? Because in the worst case, you took out one of each of the first 3 times you took out 3 separate socks, 3 separate kinds of socks, and then finally, when you take out the 4th sock, there are only 3 different kinds, so the next one must have had a pair. All right, at that point, you see it? That's the trick. That one must have been seen before, and now you got a pair of socks. All right, so that's how that works. That's a use case of the pigeonhole principle. All right, it's a fun thing to prove. Here's an even more fun thing to prove. It's the coolest, one of the coolest proofs I think of the class. I love this proof, and it just follows immediately from the pigeonhole principle. It's so cool. All right, so there exist 3 people in Fresno that are not bald, at least. There are 3 non-bald people in Fresno with the same exact number of hairs on their head. That is an absolute mathematical fact based on the pigeonhole principle. Is that not wild? Let me prove that to you. There are, I can't pick them out for you in person, but there are for sure 3 people in Fresno with the same exact number of hairs on their head. All right, and here's why. Well, the number of hairs on a person's head is at most about 200,000. So that's as most as you're ever going to get on your head. And Fresno has a population that is bigger than 500,000. And so even if you put, like everybody had a different amount of hairs on their head, like one person had 1 hair, another person had 2 hairs, another person had 3 hairs on their head. Like even if you spread them out as much as you possibly could, which is of course not true, even if you spread them out as much as you possibly could, by the time you get to the 200,001st person, there's an overlap somewhere. Do you see that? And not to mention that, like even if you try to spread them out so much, you would end up, because like on the 400,001st person, there's somewhere that you've tripled up, right? Even if you try to spread them out, like you put them all, like got a bunch of 2s now, you've tripled them up for some of them. Does that make sense? I can't tell you what the number is, but there is somewhere, like you wrap back around 3 times now. Do you see it? Because even if you spread them out so far, like you had 500,000 different people, and you're trying to spread them out as much as possible, in the worst case, into 200,000 different boxes, you take the ceiling of that division, the answer is 3, right? There's somebody, like it's 2 point something. So like there's going to be some overlap, at the very least, among 3 people, all right? That's the idea. Does that make sense to you? Because 500,000, even if you're trying to spread them out as much as you could by spreading them all out, that's greater than 2. So it's equal to the ceiling we take. It's equal to 3, and so they're all gonna match up at least for 3 people, right? There are 3 people in Fresno with the same number of hairs on their head. Does that make sense to you? That's so cool. It doesn't make any sense, but at the same time it does, because of the pigeonhole principle. All right, here's some more examples from that. Counting questions, we like, people started thinking about a lot of these questions, like a lot of these mathematical topics, they came about because people like to gamble. And so like here's a standard example of that. Like, all right, let's think about, eventually we'll get to probability in the next set of slides. But like, all right, let's pick 5 cards from a deck. You know that if you've done that, at least 2 of them must be the same suit, right? Because in the worst case, you spread it all out. The first card is like clubs, then spades, then diamonds, then hearts. you draw one more card, right? No, in the worst case, you've drawn all these. In the very worst case, you got to pick one more, and then you've got like a duplicate. That's the idea. All right, I hope that makes sense. In any order, it does not actually matter. It doesn't have to be 2 H's in the row. Like maybe it was another diamond. Okay, something like that. So I hope that's making some sense. That's just another use of the pigeonhole principle. Like in the worst case, try to spread it all out. How long do you have to wait until like you have 2 of the same suit? All right. You could have had like 2 clubs immediately, but like in the worst case, right? What happens? How long do we have to wait? That's what the pigeonhole principle is all about. All right. Here's another example. Let's pick 10 2-digit numbers, 10 arbitrary 2-digit numbers. All right. I claim that there are 2 subsets of those numbers with an equal sum. So like write down 10 random 2-digit numbers. Like, all right, 15, like 87, 21. Write down 10 of them. 33. Like make a set of them. All right. A bunch of 10 2-digit numbers. There are, for sure, 2 subsets of those numbers, like maybe these guys and all these guys, that sum together and have the same exact sum. And here's why. Pigeonhole principle. So the number of possible subsets that you could make of 10 numbers is 2 to the 10th power, right? Number of possible subsets is 2 to the 10th power. It's 1024. The number of possible sums that you could possibly have of 10 2-digit numbers, what are they? Well, if you think about it, it's like you could choose 10 0 zeros, like you could have 0 0 10 times, and the sum of all that is 0. Likewise, you could have all the way, you could have 99 10 times. Those could be your 10 numbers that you chose. And I guess I didn't need, oops. You can choose 1099s, which is 99 times 10, 90, and you can imagine you can choose numbers to make anything in between. So like the number of sums that you could make out of your 10 numbers is anywhere from 0 to 990. Yes? Does that make sense? So that's the set of possible sums of 2-digit numbers. And because this is smaller than this, there must be some overlap somewhere. Does that make sense? The number of possible subsets you could make is bigger than the number of possible sums you could have. And so that means some of these sums are overlapped in a subset. So there's two separate subsets that have the same sum because of the pigeonhole principle. There's not enough holes for those pigeons. All right, that's the answer. I hope that makes sense. It's really cool to think about. Just like very simple idea, but some very vast, all-encompassing like results. It's very cool. All right, so here's some questions for you about this. So see if you can get them all. All right, so I don't think I'll read them. I'll read them as I answer them. So please pause the video. Try to use the pigeonhole principle to answer these questions. All right, first one. How many people must be selected to ensure that there are at least 20 who are born in the same month? All right, I want at least 20 people who are born the exact same month. Don't care which month, all January or all February, it doesn't matter. In the worst case, always consider the worst case, right? In the worst case, you choose the first 12 people you choose are all born in separate months. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Tough crowd. All right. And then the next ones, they all double up just once, like another one just from all 12 months. They all double up. Now there's 2 people, right? You've chosen 24 people. In the worst case, it might just be the case where there's only 2 people, right, that match on a given month. So do you see like the game you'll have to play there? Like you choose another 12 people, they all, in the worst case, they spread out as much as they possibly can. ... I want to make sure, so like you've chosen, like you do this 19 times, right? You've built this up like with 19 people sharing. In the very worst case, they've all shared, like 19 people share a month. Only once you add one more, one more have you guaranteed that there's an overlap somewhere. Does that kind of make sense? It's like you're trying to spread out. You've got n people, and you're trying to divide them by 20, essentially. You're trying to spread them out as much as humanly possible so that, like, if you take the ceiling of all this, it's greater than or equal to 20. We just want it to be exactly equal to 20, all right? Because if you think about it, like, in the worst case, like, you've chosen 19 times 12 people, they could have been spread out amongst like, 19. Or, sorry, 12 different months. 19 of them could be, like, all doubling up 19 times. Because they could have all have been spread out evenly among 12 different months. That's still 19, right? Does that make sense? That's the idea. But if I add one more to that and like take the ceiling, Now suddenly I've got 20 overlapped somewhere. Like even if they all spread out, 19 people for all the months, just adding one more has tipped the scales. Probably you won't have to wait this long usually, but like in the worst case, you need that many people. 19 times 20, 19 times 12 plus 1. Does that make sense? That's the answer. That'll give you an overlap for sure. Ensure it that it's working. Okay, because even if you spread them out, then there's an overlap in one of those slots. All right, what about this one? At least how many people in a group of 50 were born in July? So you got a group of 50 people. How many of them were born in July? Did you get this one? This one is a trick question. There is no answer to this. There is no answer. You have no control over that, do you? This one worked because it was an arbitrary month. We don't know if it was January or February that they overlapped in, but we've ensured an overlap somewhere. This one, like, you could for sure have a bunch of, like, you could have 50 people that were born all in February. Doesn't matter. Does that make sense? So that one has no answer, but this last one does. All right. So let's assume this. So we've got a population in California is about 40 million-ish. It's going to always get bigger. So let's pretend it's 40 million right now. And the question is, at least how many people have the same 3 initials? Assume that everybody has 3 initials, first of all, because I know that it's possible for you to not have a middle name. So just for the sake of math, assume that every one of these 40 million people in California have a middle name or something that works as a middle name. All right. So, all right, try it. What are your options? At least how many people have the same 3 initials? It's going to involve this kind of like division kind of thing. It's like, if you think about it, you spread them all out. First of all, how many different sets of 3 initials are there? You could have like AAA, AAB, all the way to like your initials could be ZZZ. What are all the ways to have 3 initials? 26 to the 3rd power, right? So there's that. And then we got 40 million people in California. In the worst case, like they're all spread out, right? They're all spread out. Like as many people as possible, they all have like AAA through ZZZ, and then the next round of people, like they spread themselves out as much as possible. But what happens? You got 40 million people. In the worst case, they're all spread out among all as much as they can, as evenly as possible among these guys, 26 to the 3rd power. And then if you take the ceiling, that will tell you at a worst case, right, how many people overlap. There's at least that many people that overlap somewhere. All right, like that's kind of showing you that idea. All right, just like we were doing for the first one. That's going to be your answer. And so for fun, let's just figure that out. I would like to know. So in the worst case, right, at least how many people have the same 3 initials? At least. It's definitely not, definitely bigger than what we're about to find. There's 40 million, I think. Yes. Divide that by 26 to the 3rd power. At least, we take the ceiling, right? So 2,276. Interesting. People on the low end at least have the same 3 initials in California. There's plenty more than that because more names, like you know that certain initial combinations are more common than others, like John Smith. There's a bunch of John Smiths. There's a bunch of J blank S's sitting around in California, right? So yeah, I think that's what I wanted to say, and that's how you find it. I hope you see that. So the pigeonhole principle is a very cool idea, and it's a great place to end on in our study of counting. And I think that's all that I wanted to tell you for these slides. So thank you for your attention, and I will see you in the next one.